All right, this is Mr. McMurray again. We're in chapter 4. We're going to be talking about Newton's third law. Okay, Newton's third law is also called sometimes action reaction, but we'll talk about that in a second. Now, if you push against the wall, how many forces are being exerted? Normally, most people would say, well, you're pushing on the wall, so you're exerting a force on the wall. All right, but what Newton realized is that forces are an interaction. It's not a one-way street. It's an interaction. That means there has to be something interacting with something else. So in that case, it's my hand and the wall. Okay. For example, the guy here showing I'm holding up the wall. All right. Now, if there were just one force and he was pushing on the wall, then what must happen? Well, the wall should move, or there should be a net force of greater than zero, and according to Newton's second law, there should be some acceleration happening here. Okay, or Newton's first second law, it should accelerate. But does the wall accelerate? Does it move? Does it go anywhere? No, it does not. Therefore, we know that the net force must be zero. Okay, so there must be some force that's canceling out the force we're putting on there, and therefore giving us net force of zero. And the fact is, if you look at your hand, when it pushes back, you'll notice that your hand flattens out and whitens. Why? Because the wall is pushing on it as well. And so for every force, there's a pair of forces actually. Okay, if I push on the wall is also pushing back on my hand. This is why if I slam my fist in the wall, yes, I'm exerting a force on the wall, but my hand is going to be all bloodied up. Why? Because the wall is also exerting a force on my hand. Okay, and so therefore there's always two forces going together, and they occur in pairs. Now, we also tend to think like that we talk about a ball. Say I throw a ball. Well, I exert a force when I throw it. My hand is pushing on the ball, and the ball is also pushes back against my hand. But once I let go of the ball, does it have force? And the answer is no. Forces are something that we can exert on an object. Once the object is moving, Newton's first law kicks in. It will continue to move until a force acts on it. Okay, it moves at a constant speed, constant velocity, until something acts on it. Air resistance, for example, could slow the ball down eventually. But we can't say that the ball, as it's going through the air, has a force. It's not a property or a part of the object. Like it can have a speed, it can have mass, but it can exert a force. When that ball hits something, it will exert a force on it. It's exerting a force on the air, and the air is exerting a force on it, which could slow it down. Air resistance as it's going, but we can't say that the ball has force. A force is something that is exerted. Okay? Now, when there are these two forces, then we say there are action forces and reaction forces. Okay? And they are equal but opposite. And that's what Newton's third law says. For every action force, there is an equal and opposite reaction force. Now, someone says, for example, if this big semi-truck loaded with a heavy load of, we'll just say garbage because that sounds interesting, and it's smelly and all that. All right, if it hits a small vehicle, all right, which one has more force or feels a greater force of impact? The correct answer is they are equal and opposite forces. Okay, so the truck exerts a force on the car in this direction. The car exerts a force on the truck in this direction. Notice the force that's exerted is equal. Now, are the results of the force equal? No, because the car has a very small mass and the truck has a very small mass. And a big mass, or a very big mass. And so according to Newton's second law, there's going to be a big difference in the effects or the acceleration, how they change their speed and direction, because it also depends upon the mass of the object. And if something has a small mass, then it's going to have a big change in acceleration, or in this case, deceleration in the case of the car. Okay? And so the effects of the force may be quite different depending on the mass of the two objects. But the force that the truck exerts on the car is exactly equal to the force that the car exerts on the truck. Okay, the effects of the force may not be the same, but the force will be the same, and that's something we have to keep in mind. That's a little confusing sometimes because people think about the effects of the force. All right, now say we have a hammer nailing pulling a hammering a peg into the ground. Sorry, there we go. And so normally we think the force is the hammer exerting a force on the stake, but technically the stake is also exerting a force on the hammer. If you were to look at this in slow motion, every time you hit the nail or hit a spike, you will see that the hammer bounces up as well because it has a force exerted on it, an equal force to the force that's being exerted onto the peg. And so both of them are having a force exerted on them. All right, now that's why we usually have a fairly heavy head on our hammer so that it has more mass and it is not affected by the force as much as hopefully the nail. We want the nail or the peg to go in a lot farther than the hammer bounces back off of it. Okay, but that has to do with the mass and the effect. Now, which one? It could be argued that, well, the peg is the action force and the hammer is the reaction force. And really, in truth, since they're pairs and they always go together, it really doesn't matter which one we call the action force and which one calls the reaction force. Okay. Usually we talk about, in this case, we want the hammer to drive the nail into the ground or the peg. So we tend to call that the action force. But really, there's not one that's the action and reaction. If you call one the action force, the other one must be the reaction. But since they're equal and opposite in opposite directions, then they're going to be considered basically the same thing. All right, this is very similar to what's called Newton's cradle sometime, or there's other names for it, but you've seen it where you drop the ball that hits it and it causes the other ball. Usually you have about 3 of them here so they get passed on. But basically, if you drop this ball with string, it has speed and velocity. Okay, when it comes and it hits the other ball, okay, it exerts a force on the other ball, and the other ball will bounce off at almost exactly the same speed and velocity that this ball had. However, if it just exerted a force on that one, then it would continue to move. But it doesn't, because this ball, when they hit, when this one comes in and hits this one, it exerts an opposite force on that one. And since it's opposite, it's just exactly cancels the force. It's in the opposite direction. The ball is moving like this. When it exerts a force on it, it's this direction, the opposite direction. So it stops this ball, it exactly cancels out its motion, and then this one begins to take the same speed and velocity. Now, it will go up until gravity, a force, acts on it, and it slows down, and then it will come back and hit this ball again. Once again, equal and opposite, so it will cancel the movement of this ball, because it'll be pushing against it in this direction, and this one will hit that one in that direction, which will cause it, since it's sitting still at the moment, it will cause it to go in the opposite direction. Okay, and so at equal speed and velocity. And so this is kind of why it's a neat thing to watch it go back and forth, but that's basically what's happening in that reaction. All right, let's look at some action-reaction for examples. A lot of times, like I said, we think of forces as just one force, and we don't think about the other force that has to accompany it. So, for example, if you have a car that's pushing on as it goes down the road, the tires are pushing on the ground, and the ground is pushing back. So you can either say the action, like once again, it doesn't matter which one's the action or reaction, but the wheels are pushing on the ground and the ground are pushing back, which pushes the car forward. Okay. If you have a rocket, rocket's one of the most common examples that we think of. Rockets are made possible basically by Newton's 3 laws, and as the rocket burns fuel, the exhaust pushes against the rocket this way, and the rocket pushes it back that way. Pushes the air out this direction, exhaust out that direction, and so you have this action-reaction, which pushes the rocket forward and the exhaust out the back. For a long time, people thought, oh, if you go into outer space, there is no air out there. But the point is, the air is not, in order to make the rocket go, the air doesn't have to push against the air or something out here. As long as there's air in here where the rocket's reacting, and it, as a reaction, as the fuel burns, it creates air, it pushes that out. That pushes the rocket in the other direction. It does not matter if there's any air out here or not. But there were, when it first said that they were going to use rockets to go to the moon, there were editorials in large papers like New York, I believe the New York Times, but New York Post, that said basically this is the kind of ridiculous watered down physics that people don't understand the basic rules. There is no air in the space, and so there's no way rockets will work in outer space where there's no air. But once again, it does not involve what's out here. If it's when the fuel burns, it shoots out the gases this direction, and that pushes the rocket this direction. So you have these action-reaction forces, and you don't need atmosphere in order for that to happen. Okay, same thing. If he's pulling on a spring, the spring is also pulling on him. That's why as soon as he lets go, the spring goes back, because both are exerting a force, action-reaction. Now, gravity is another one. When you drop a ball, obviously the earth pulls it toward the earth, but technically the ball is also exerting a force on the earth. It is pulling the earth toward it. So it says, what? Yes, if you were to jump off a building, yes, the earth pulls you down toward it and possibly break a leg if you don't have some kind of safety thing. But you are also exerting a force on the earth. The problem is you have a very, very small mass. So you are affected by the earth's pull of gravity. The earth has extremely large mass, and its mass is largely unaffected by your force. Kind of like we talked about the truck and the car hitting. Okay, except for this time the earth is a humongous truck, and you are an extremely tiny little thing. And so it's kind of like a flea or a fly running into an elephant. Okay, yes, the fly would exert a force on equal force on the elephant. The elephant would exert on the fly, but the fly is going to feel it a lot less, a lot more. Whereas the elephant's not going to be affected by it because it's such a small force on it compared to its mass. Okay, and the same thing. So you are actually pulling the earth just as much as the earth is pulling on you, but it doesn't affect the earth very much because it is so big. Okay, and this goes back really to Newton's second law. Okay. The effects of the equal forces are very different on the objects because they have different masses. Okay, and so, for example, if we were to look at a cannon, all right, when you fire a cannon, it exerts a force on the cannonball, but Newton's third law says there must be an equal force. Not only does the cannon, as the gunpowder explodes in here, exert a force on the cannonball also exerts a force backwards against the cannon. Okay, so there's an equal force, but the cannon has a big mass. So the force divided by a big mass gives you a small acceleration, and that's kind of like the kick of a gun, a rifle. You fire a pistol. In the case of cannons, when you see them in the movies, they shoot and they kind of go back a little bit, recoil, okay, or bounce back. So it does move a little bit, but you don't want it to move very much because obviously then it would hurt people behind it. Okay, so it moves that because it has a large mass. Since there's a large mass, you divide that force by a large mass, you get a small acceleration. The cannonball, on the other hand, has a relatively small mass. So you take the same force, divide it by a small mass, and you get a lot faster acceleration. Now, someone says, well, what if we got bigger and bigger cannonballs? Well, as the mass gets bigger, it becomes closer, and so you would have a cannonball and a cannon that would start to accelerate at the same rate, and that would not be a good thing, okay? Because you don't, your cannon, I mean, eventually you get to the point where you had a cannonball that was so big that actually the cannon would move more or accelerate faster. That would not be a good thing, all right? So basically, the effect of the equal forces depends on the mass of the two objects. Right? Which leads us to this. The important thing about opposite and reaction forces are that they are exerted on two different objects. One object's exerting force one direction, the other one's exerting the other direction. For example, if you kick a football, okay, the foot exerts a force on the football, but the football also exerts a force back on the foot. Okay, and those are the opposite and equal reaction. Now, so it says they're opposite and equal, they cancel each other out, but the point is, the football exerts a force on the foot, and there is nothing to cancel that, and so the foot would either slow down, change in acceleration, or possibly even bounce back a little bit, depending how hard you kicked it. Okay, now the football, on the other hand, has an equal force. The same force being exerted on the foot is being exerted on the football, but once again, the only force exerted on the football is this direction, so it's going to go in that direction, okay, because it's an unbalanced force, okay. So when we have these action-reaction, notice that they are acting on different objects, okay. The foot kicks the football. When you kick a football, there's a force exerted on the football, and there's a force, equal and opposite force exerted on the foot. Okay. Now, my question is, if you have a situation like this one up here, where you have two people kicking the same football at the same time. Is this an example of opposite reactive forces? Stay tuned next time to find out the answer.